Welcome students of class 11 once again. We are on the chapter that is thermodynamics. In the previous classes we have discussed on the different thermodynamic parameter, thermodynamic work, and also some relation in between the thermodynamic parameter and we know the basic concept of thermodynamics. Now in today's class I will discuss on some definitions regarding to the change in state or such kind of parameters. So first of all, it is the enthalpy change of the reaction. It is symbolized as enthalpy change of the reaction. Enthalpy change of a reaction. It is symbolized as delta RH, and if it is given in the standard state, then the denotation of V, or sometimes delta HRH at the standard state. So 0 or V indicates that is they are in standard state. What is this standard state means? Standard state means there is a optimum temperature and pressure is maintained during this reaction. Now second, that is what is the mathematical expression of that, is delta HR delta RH is equal to standard enthalpy of the product and standard enthalpy of the reactant. So if a reaction, that is A plus B equal to C plus D, then more than one product is there, then we should write down summation of I, that is AI, that is for the product, AI of HP minus summation of BI reactants, delta H of reactants, delta H of reactants. So this is the mathematical expression of delta HR. Now if more than one reactants or products are there, then we have to sum up, because the difference in enthalpy is equal to the individual enthalpy change of the reactants and products. For example, if we take the reaction, that is CH4 plus 2O2, CH4 plus 2O2, CO2 plus 2H2O. Now for this reaction, delta H of R, that is equal to the reactant, that is change in enthalpy, H of M CO2 plus H of M H2O, that 2 times that of H2O minus H of M of CH4 within bracket plus 2 of H of M of H of G of O2. So this is the overall change in the enthalpy. This is from the product and this is from the reactant. So it is the expression for the enthalpy change of a reaction. Next, that is, what is standard enthalpy of a reaction? Standard enthalpy of a reaction is defined in the same kind, but standard state, I just mentioned standard state, that is there is a optimum temperature and pressure is maintained. So when the reactants and products are in standard state, then the enthalpy change in the product minus reactant is equal to the standard enthalpy of the reaction. and the condition is temperature maintained. Temperature is equal to 0 degree 270, that is minus 273 degree centigrade, and pressure is equal to 1 bar, that means atmosphere pressure, that is at 0 degree Kelvin or minus 273 centigrade. It is the ideal condition of standardization. Enthalpy change during phase transformation. We know the phase transformation, that is it is from the solid state to liquid state or liquid state to vapor state. Now enthalpy change during phase transformation comes with the sign, that is when the energy is supplied to the system, then it is del H is positive, that is it is endothermic in nature, and the reverse case, that means when energy is evolved from the system, it is negative, that is it is for an exothermic reaction. Now standard enthalpy of formation is equal to standard enthalpy change for the formation of 1 mole of compound from its element in their most stable state of aggregation. So it is the definition of standard enthalpy of a reaction. Next one, there are definition regarding to this chapter. Then what is enthalpy of fusion? That means fusion is also a process, that means fusion from solid state to liquid state. Now fusion, that is here we should also maintain the standard state and also at the temperature. So the definition of fusion is enthalpy of fusion is the heat change or change in enthalpy when 1 mole of solid at its melting point is converted into liquid state. So what are the parameters? That is at the point, at a fixed point, that is its melting point, and the process is known as melting. So this is the definition by change in phase transformation, that is enthalpy of fusion. Now it is also the phase transformation from solid state to liquid state. Now for example, enthalpy of fusion. Enthalpy of fusion, for example, enthalpy of fusion of ice. Fusion of ice at 273 K is 6.0 kilojoule mole inverse. Now H2O solid to H2O liquid. It is the phase transformation. So delta H fusion, delta H at standard state is equal to plus 6.0 kilojoule mole inverse. It is the representation of enthalpy of fusion. So enthalpy of fusion is the phase transformation from solid state to liquid state. We can represent by the delta H fusion. Next, that is enthalpy of vaporization. Enthalpy of vaporization is the process when 1 mole of a liquid vaporizes completely into gaseous state. So enthalpy of vaporization. Here also we go with an example, enthalpy of vaporization, that is example H2O liquid to H2O gas. Here standard vaporization of enthalpy at standard state is equal to 40.79 kilojoule mole inverse. Now if we follow the data, it is plus, that means here an amount of energy in the form of heat is required to this transformation. And from the physical aspect, we know that from the liquid state to gaseous state, there is the energy should be given to the system. Next, that is enthalpy of sublimation. Enthalpy of sublimation. So sublimation is the process from solid state to gaseous state. So when a solid state undergoes a change to the gaseous state, the example, that is iodine solid to iodine gaseous state, here that is enthalpy of sublimation H at standard state for this process is equal to 62.4 kilojoule mole inverse. This is the process that is enthalpy of sublimation. Next, standard enthalpy of formation. Standard enthalpy of formation, that means when 1 mole of a substance is produced from its constituent, then the change in heat content or change in energy comes under the standard enthalpy of formation. Standard enthalpy of formation, that is delta formation it is a representation of that. Example, that is carbon plus 2H2 CH4. So carbon plus hydrogen, hydrogenation of carbon, formation of methane, that is here delta H formation is equal to minus 74.8 kilojoule mole inverse. So it is, there is, we know that there is a energy is evolved from the system, and it is the formation of CH4 from its constituent is known as standard enthalpy of formation. Enthalpy of combustion, that means when 1 mole of substance is burned in presence of air or oxygen producing the compound and energy, this comes under the enthalpy of combustion. For example, CH4 plus O2, CO2 plus 2H2O. Now here enthalpy of combustion, standard enthalpy of combustion. So here standard enthalpy of combustion for this process is equal to minus 890 kilojoule mole inverse. So here large amount of heat is required for this process. Now the importance of this process or the importance of this word is when there is a problem or we have to take the energy change for a industrial process also, or the heat energy required for a process, we should go with this mathematical expression. Next one, what is thermochemical equation? So thermochemical equation is the equation when it is represented in the with the state of the individual component with its stoichiometry and the heat evolved. So what are the points? First of all, the stoichiometry. Second one is the state of the reactants and products, and third one is the heat evolved or heat absorbed by the system. For example, thermochemical, the terms, that is thermal change during any chemical process. For example, H2 gas, so it is the state, plus half of O2, it is also gas, forming H2O, it is liquid. So here the delta heat of formation is equal to minus 286 kilojoule mole inverse. So when we represent it in the thermochemical equation, so thermochemical equation will be H2 gas plus half of O2 gas forming H2O liquid minus 286 kilojoule. This is the expression of the reaction in thermochemical form. We have earlier discussed, that is Hess's law of constant heat summation. Next one we have to discuss, that is what is Born-Haber cycle. Now for an ionic crystal it is not possible to determine the overall change in the heat content throughout the process, because ionic compounds follow a 3, 4 or 5 steps to go to the compound state. So for this reaction we have to go through the stepwise method, and for this there is the term that is Born-Haber cycle. That means from the constituent to the product, the every steps or calculation of the enthalpy in the every step is present in the Born-Haber cycle. So in Born-Haber cycle there is the we have to take the example of sodium chloride. Born-Haber cycle. Example, that is sodium chloride. So taking this example, first of all state sodium solid state to sodium gaseous state. It is called energy of atomization. Energy of atomization. Second step, it is delta H sublimation is equal to 108.4 kilojoule mole inverse. It is the first step. Second step will be in a gas, sodium gas to sodium plus. Here also the energy is required is equal to ionization enthalpy, that is delta I of H is equal to 496 kilojoule mole inverse. Right? Now number 3 step, that is half of Cl2 to Cl gas. Here it is also the bond dissociation, half of delta of bond is equal to 121 kilojoule mole inverse. Next point, that is now step 4, that is Cl gas to Cl minus. Cl gas to Cl minus plus electron. This is called electron gain enthalpy, that is delta electron gain is equal to minus 348.6 kilojoule per mole inverse. And step number 5, that is Na plus Cl minus forming NaCl. Here it is the gas, it is also gas, NaCl is the solid. It is the lattice energy or U is equal to unknown. Now these are the steps we have to follow. Now for the calculation of lattice energy, is equal to delta H lattice H is equal to, at standard state, is equal to 411.2 plus 108.4 plus 121 plus 496 minus 348.6. It is equal to plus 788 kilojoule. So we have to add the every step to calculate the overall change in enthalpy for an ionic crystal, and it is comes under the Born-Haber cycle. On the next day we will discuss on the spontaneity, what is spontaneity, and the second law of thermodynamics, and also the free energy function, and also entropy. Thank you.